So we had green theorems, Stokes theorems, and why are they so special, right? We had the fundamental theorem of line integrals. That was and we had randomly two people's last names here. Why are they important? Yeah. So Stokes theorem was after green, and like if you want to do some history, okay. Now the cool thing about green theorems and Stokes theorem is, right, Stokes was like, all right, I like green theorems, pretty cool over line integrals, that kind of makes sense, but I want to apply it to higher dimensions because these smart people can actually see multiple dimensions. Don't know how to do it, but they can do that, or theoretically how to do so. So little review. Right, so Green's theorem related line integrals, right? That was the biggest thing. Line integrals of planes to double integration over regions, right? That's what he said, right? The curvature itself creates a line integral from there. Now Stokes' theorem says, well, okay, why don't I apply that to 3 dimensions? So not only does a line integral represent a region, right? So again, this is what Green's theorem said. If I have a line integral connected, creates a region, and I can find anything I want over that region, right? I can integrate, find the volume, and all that fun stuff of this region. Again, this is in 2 dimensions. Stokes' theorem said is, okay, I think this also applies to 3 dimensions. Okay? So what he said is he wanted to relate surface integrals, what we just did, over the surface S to line integrals over the boundary of S. Meaning, again, if I am literally looking right on top of this figure, right? Note that means I don't see what Z is. It's flat, just like if you're just looking at a door. And you see this line integral is just the output of the surface because, again, you don't see above or below, it actually is. Okay? So really, he was like, okay, it looks like a surface integral can be represented as a line integral, which is even better because sometimes line integrals could be easier to apply, or sometimes surface integrals would be easier to do than line integrals, and vice versa. I know you guys probably disagree, but yin and yang, right, when it comes to it. So that's the process here. So given the surface, if I look straight ahead, this now becomes just a simple line integral. In other words, Green theorem actually does apply. Okay? Now, what Stokes' theorem was actually able to do was do even more of that. He was able to say, if S is an oriented, let me talk about oriented. So oriented smooth curve basically means it's as an orientation. You know what that means, right? It goes in one direction of this curve, and it's smooth, meaning it's an actual closed portion, right? We talked about closed simple curves before. That's all it means. Okay. So in other words, it's going to look like that all the time, okay, or some version of that. Okay? So given this, when some curve with positive orientation, let F be a vector field whose partial derivatives are known in the R3, so you could take the partial derivatives right there. They're not like, limits don't exist. Therefore, this is the key thing. The line integral is equal to the double integral over the surface of the curl of the vector field. That's the interesting part. So we have a line integral. Right, this is 1 dimension over C, right? This is the line integral over C, is equal to the surface integral over a surface. Which means we can go from 1 dimension to 2 dimensions and vice versa, however we choose. So now, therefore, some of these horrible, like you saw, surface integrals can be simply broken down to a simple line integral of 1 dimension. And vice versa. A really difficult line integral can now be created into a double integration with a curl, which makes the surface, the line integral easier to do, and vice versa. Now, this was such a good revelation that just like line integrals, when it comes to green theorems, we have like a circle, if we're going over circles, same thing applies to Stokes theorem. So quick little notation is whenever we're using Stokes theorem, instead of going over S, we use a simple integral called ds, like that. It's so popular it looks like that. So whenever we deal with the Stokes terms of the curl itself, instead of using a double integral, they also use that, the single integral ds. It represents a double integral, just for notation purposes. And I always give it to you like this, don't worry, but your book does it like this. Okay, so we just found out Stokes theorem. You can find a line integral using a double integral curl. So guess what? Let's put it to action. Let's see if it actually is making it easier. So let's find the line integral of f dr, right? The vector field time dot product dr, where our vector field is equal to this, and our curve is the intersection of the plane y plus z equals 2, and the cylinder x squared plus y squared equals 1. Okay, now this actually is not that bad to actually graph. So since we have a cylinder is not too bad to graph itself. Let's suppose we have a cylinder and we have a plane, right? So let's say this is our plane here. So it cuts it. So essentially right where it cuts it, it's going to be a circle. So we have I want to put it up like this. It's not going to be exactly flat. There we go. So that plane cut it like that. Okay. So now we have an orientation, right? We have a curve that it's made. So this is our C, and this is our surface S. Okay. So in our definition, our curve is the intersection of it. So this is the curve we're talking about, that little oval there, or ellipse. And our surface represented as, or our vector field surface is right here. Oh no, that's a surface cylinder. So we want to figure out the line integral of this there. Well, we just learned Stokes theorem, so why don't we just apply it? Okay. So Stokes theorem says I got to find the curl of f. So just in case don't remember, the curl of f is the cross product of the gradient times f itself. Okay. So that's actually not that difficult to find. Three y squared x and negative 2z squared. So we just find the determinant, right? So it's going to be, all right, so with respect to y, 0. With respect to x, 0. Don't you love it when you get zeros everywhere? Okay. With respect to x, also 0. With respect to z, also 0. Even better. All right, and then k, okay, we actually have to do stuff, right? So with respect to with respect to x is going to be 1, minus with respect to y is going to be 6y. Okay. All right, so our curl is just 1 minus 6y in the kth direction. Oh, so lovely when things cancel out, right? It comes to it. So this is going to be the double integral of a region, or sorry, our surface of 1 minus 6 in the kth direction times ds. I don't know how to do this. Well, there's two different ways we do this. We'll say that. Either way, you're going to get the end result. We're going to talk about an example of this probably tomorrow. But one way to do this is you multiply by k again. So in other words, you multiply by this one again, and you take that integral over the region. But I really want to do this because look what we have, right? Work smarter, not harder. This curve is a circle. or kind of a representation of a circle, right? Let's just cut it. So I can use polar. Now you may be wondering, this makes it harder, but actually it doesn't. It actually makes it a lot easier to deal with. So since we have a circle, radius 1, and again, going all the way around. So this becomes the integral from 0 to 2 pi and 0 to 1 of r times all this. Remember, so you guys remember, I'll just leave it as well. Y is r sine theta. So the r times r squared sine theta, because again, we have to multiply by r, dr d theta. So integrating in respect to r gives you r squared over 2 minus r to the third over 3 sine theta, evaluated at 1 and 0. Same thing, you plug in 0, everything goes away. So this is just going to be the integral from 0 to 2 pi of 1/2 minus 1/3 sine theta. Oh, missing something. Oh, missing the 6. Oh, no wonder. Something didn't look right. Yeah, okay, good. Okay. This is 1/2, yeah. Right, so integrating with respect to theta, this is going to be theta over 2 minus, this is 1/2, so it'll just be 1/2. Integral of sine gives you a positive. Evaluate it at 0 and 2 pi. Right, plug in 2 pi into here, you would just get pi plus, plug in 2 pi. Cosine of 2 pi is 1, I believe. Yeah, and then, oh no, this is a 2, 2, 1, 2. Is a 1. 2 times 1 is 2. Plug in 0. Plug in 0 for cosine, that's 1. So that also gives you 2. And oh, positive. Yeah, what am I thinking? Maybe my sense messed up. Okay, so good. So this is what then. So I get pi plus 2 minus 2 just gives me pi. There we go. Questions here at all of using Stokes theorem? Hopefully you notice the integral is actually much easier instead of using actual line integral, because we'd have to do the same thing and convert it to, in this case, cylindrical coordinates and find the integral from there. So good. Okay, so I do have time for my last example, because the last example, believe it or not, actually is pretty fast, even though you have all the space here. You're going to see it. So, all right. Use both ways of Stokes' theorem to find this, where the vector field is that S is a part of the sphere of, oh boy, x squared plus y squared plus z squared equals 4, lies within the cylinder x plus y squared equals 1, and above the xy plane. Okay, this one, it's very hard to see what's going on. So this is what it is. So we have the sphere, or especially half sphere, because you want it above the xy plane, and we have the cylinder here. Okay, so our curve is going to be this part that intersects it, and it's above it. So we have some z distance from this point to that point as well. We got to talk about as well. Okay. Now, what do we mean by both ways? So both ways of Stokes theorem is saying, I'm going to first do this. So do what we just talked about, we did it. And I'm also going to do the line integral, the old-fashioned by the definition of it. Okay. Now you may think, oh boy, but it's actually not as bad as you may think, because you should get the same result, right? Right, that's the whole point. So we're not going to prove Stokes theorem in general, but we're going to prove it as an example to show it does actually work out. Okay. But who knows? If you could find one that disproves it, you'll be rich upon your wildest dreams, because everybody thinks Stokes is the most important thing, pretty much one of the most important persons in most binomial calculus. But anyways, let's do our curl. All right, so let me put them here so you can see what's going on. So one, we're going to show that this is true using this way. And in the second way, we're going to find the line integral of that. That's how we're going to do both ways. Okay. So first off, we just do like the last example, find the curl, and then take the integral. All right, so our vector field is xy, or xe, yz, and xy. Okay. So what do we get? So with respect to y is x, with respect to z is y. With respect to the j, so x with respect to z, no, it's the y. X. And then the last one, with respect to x is 0. And then with respect to y is 0. Okay, so our curl is going to be x minus y I. I'll print this inside, so it's going to be plus x minus y j. Right, and the k is gone. Okay, so therefore, we're going to find the double integral of a surface of our curl times dx. Okay. Now, I kind of hinted this last time, right? But in order to find the actual double integral, we need this in terms of just one single kind of like polynomial, right? So what we're going to do is we're going to multiply our curl times k, the kth component of our curl, okay? So therefore, we have one straight integral. So if I multiply our curl, which is just going to be, or not multiply it, but dot product itself. This dot product. And what's our kth component? 0. This is interesting. Does that seem right? Oh, sorry. This is going to be, well, get the same result, but what's my k component? xy. And this is the k component. So if you're wondering what I meant by that, right? The kth component is 0, 0, that. This is only the kth component. Well, 0 times that is 0. 0 times this is 0. And this times 0 is 0. With respect to y is x minus with respect to z is y. I think that's right. I think that's where you're asking that. Oh, j. J. With respect to x. Oh, I've inserted the negative. That's what you're wondering. So just change it to signs. I think that was your question, Gabriel. But anyways, hey, that's 0. And we just talked about this. What is that equal to? Everybody should saying that unanimously. 0. Okay. Well, hopefully, if we do the other way, we get the same thing. So let's find out. All right, so this time, number 2 now, we're going to find the line integral of f dr. Now, the best thing is, this is a circle, which means we can use Green's theorem. So Green's theorem says we got to first find a parameterization. So we'll use the general one. So x equaling r cosine, y equaling, the circle one. Now, here's the issue though. Oh, actually, we'll just start there for now. And we can use theta. I just use t because I have to use Green's theorem. Now, the problem is the z term. Okay. So I hinted this last time, right before. What is the z value going to be? Okay. So this one, we're actually going to have to solve for z, meaning we're going to solve for z, putting it right here. So we're going to do this. It's going to be x squared plus y squared plus z squared is equal to 4. And x squared plus y squared equals 1. So notice if I just, set multiply by -1 and just solve for z, those cancel. We just get z squared is equal to 3. So z is equal to the square root of 3 in this case. So that's going to be our parameterization there in terms of just a term, right? Because we only, remember, the line integral is only one variable. So we can't have it just x and y. So that's how we get that z term there. All right, now, next step, we got to find f at our parameterization vector. Okay, so this ends up being, plug it back into here, x times z, so square root of 3 cosine t, y times z, and then yx, so cosine t sine t. Okay, next up, right? So remember, this is equal to the line integral of what we just did, f of x times the derivative of t, right? We did that way back in the day. I expect you to memorize it, but we actually did that. Okay. So next step in our integration is just take the derivative of this individually. So this is going to be negative sine, positive cosine, and that also is 0, right? Because that's not in terms of t. Very interesting. Oh, maybe we have that before. Very interesting. Well, let's just keep going. Who knows? Maybe we'll get rich and break his theorem when it comes to it, right? We all get rich because of it. All right, anyways. Now let's do this. So we have everything we need, right? We have this, we have that. So now we're gonna make the dot product of this line integral. So we're gonna go with the integral. Well, we'll just make the dot product first. So it's gonna be f of r of t dot r derivative of t. So it's going to be this times this, this times this, this times this, all added together, right? So that times that. Oh, chill. Put it over here instead. That times that. And then this times this, which is 0. Well, what happens when we add everything up? What do we get? We cancel out. And we just talked about this. Doesn't matter what our line integral is. Integral of 0 with any variable is still going to be 0. So look at that. It does work in any direction you want it to.